So now we come to the last of the use case classifications. And remember, we'll just divide them into three just to give you a breathing room because you're bored already, are you not? We don't have too many more slides, and then you can relax and listen to a different MOOC with a different speaker so you don't get so bored by my toneless voice. So let's go for it. 4 more to go. I thought maybe 5. Okay. Here we have classification, which is as I pointed out, many of the use cases, I think it was around 20, involves classification of some sort. And here I'm using in the very broadest terms. Search classifies documents by the nearness to your query. Recommender systems classify items by the relevance to your interests. So these are, so I'm using the word classify in the English sense, possibly not in terms of a computer science sense. When you do network science studies, you study communities and how how the internet links people together through friends on Facebook or websites they access into like-minded folks. So that's classifying people into communities. Biologists classify sequences by their role, what the disease that particular gene is associated with, and also to the biological family and species and genera to which they belong. Machine learning, which is another important classification, effectively implements classification in several ways. So there's things like support vector machine, divides data into regions using planes, clustering divides the data into groups where the members of each group are near each other. Notice clustering is unsupervised learning as there's no input as to categories. Collaborative filtering is essentially supervised learning as it uses existing rankings to predict new rankings. Learning networks typically use existing classifications, although there are also unsupervised, which is discussed in use case 26, unsupervised learning networks. But supervised learning networks take a set of training data, which where the answer's known, and uses a whole set of data with known answers to train a neural net, which then can take a case where the answer is not known and give you the right answer. So classification is very important. So we've done a bunch of other features, and there are a couple we haven't done directly. One is Monte Carlo, which is the generation of random data that mimics observed data. And as I mentioned earlier, it's used to quantify analysis by testing the method and determining their efficiency. And in particle physics, the Monte Carlo data actually needs competitive with the observed data. That's partly because you're trying to find efficiency when you observe the Higgs. You want to find out the properties of the Higgs. So you look and see what the Higgs does. Well, maybe remember these, although your apparatus cost whatever it did, $50 million, well, that's probably an underestimate. It's still not perfect. And there are certain particles that you do not observe very well. And so certain decay modes of the Higgs you don't actually observe very well. So you find out how well you observe each decay mode using Monte Carlo, and you then use that Monte Carlo to take the observed rates and then correct them for the events you would miss. And you find out very straightforwardly what the probability of observing a particular Higgs is in a particular mode. You just generate that Higgs in a Monte Carlo in the types of events which are similar to the ones observed, and you run that Monte Carlo data through the entire software from beginning to end. And then you just ask how many of those events you found and how many you missed. That's very straightforward. But it requires a lot of Monte Carlo data because to get accurate answers, because uh, you're effectively dividing by it. And if you have a small number divided by it, it can produce you big errors. So you want to get accurate answers for efficiency, you tend to need a lot of Monte Carlo data. We've already stressed streaming and the Apache project, Storm, S4, and SAMSA. And obviously, when I go to e-commerce site and I can be thought of as streaming if I'm the first time I've ever been to that site. They won't know anything about me, but they can still do a useful job on me by doing an algorithm appropriate for such a new user who is added to the information calculated in batch mode from all the previous users. If we go to particle physics, you could think, well, maybe we do streaming for that type of case because we have events. Each event is produced one after another because the accelerator keeps on chugging away, and each event corresponds. There's maybe hundreds of events at each time the accelerator collides. That they're effectively individual events that you can analyze separately. And but it's not really the same because you don't actually analyze data event at the time when in use case 39. Rather, you take a lot of data from a so-called run. You're doing a physics experiment. You have your apparatus. You lovingly get the apparatus running. And then you have the accelerator. You lovingly get the accelerator running. And then you do this. Then you take some data. And that's the run. And that run will have its own special features and its own calibration. And you need to do a correlated analysis of all the data to be able to efficiently use that data. And you usually have to put in some, at least when I did this work, we had to fix the software for particular runs because it had something was broken or something was not quite right and things like that. So the stream model, that's a sort of, then we have an incremental model. We take one run and add a new run, but each of those runs is a large amount of data. So it ends up not being like streaming. We have a famous slide which will come on, which we'll do, which is the following slide. It characterizes the various versions of MapReduce and also pleasingly parallel, which is a so-called map only, which is a special case of MapReduce. And so we have these actually 5 types of MapReduce now: pleasingly parallel, MapReduce, MapReduce stats, MapReduce, ITA, and HPC. So those are all variants of MapReduce with slightly different structure. In each case, they have an overall, the same thing which we've already discussed many times: single program, multiple data, divide the thing that's big up, and use lots of processes with each process running the same software, tackling part of the problem. And then this is all done over the particular data set with a particular form of parallelism. Then in each case, the calculation done is a map, and then the communication is the reduce. And in the case where there's effectively no reduction, is map only. The case of MapReduce has one set of maps followed by one set of reductions. MRStat I just put down because it's quite common, where the reductions are really simple, global averages, so they really take no time. At least say in that particle physics case, the global averages are very fast compared to the 10 seconds it takes to process an event. We've mentioned that iterative MapReduce is an important concept because when you do so-called expectation maximization and parallel linear algebra, you always have multiple waves of maps followed by reductions. Because you're iterating, you do not have one map followed by one set of maps followed by one set of reductions. You have map, reduce, map, reduce, map, reduce, And you need to save the data in memory between the different stages. And then finally, the other class we have is high performance computing, which is single program multiple data, but the communication is typically not reductions, it's point to point, and the messages tend to be quite small, and there's a lot of efficiency needed in programming and the hardware to be able to make message passing efficient for small messages. Here's this picture, shows PP is or MapOn is A, MapReduce and MapReduce Stat are the classic MapReduce. MapReduce Iter is C, and a high performance computing or MPI is D. And we have the structure illustrated here, just maps. We have maps followed by reductions, maps followed by reductions, and then we loop back after reductions, have a new set of maps, new reductions, and loop back again. And in the case of HPC, we have local point-to-point communications, not reductions. So we know the last set of discussion corresponds to the actual analytics used, which is this library, like Mahout for the Apache Big Data Stack. And so this is in the case of the title of the class, Application Analytics, this is the analytics. I noted there were two important styles of analytics, global and local, depending if the analytics is really focusing at each analytics goes on one point, or the analytics crosses all points. And with pleasingly parallel applications, we have this, like in the particle physics, you have a local computation, which is the really messy, takes 10 seconds for the average event from Atlas and CMS. If you do heavy ion collisions, it takes a lot longer, in fact. And so that's one case. When we go to Iter, MapReduce, Ego, and expectation maximization, those require global machine learning. And typically these are where non-trivial parallel algorithm work is done, and it can be challenging both for algorithms or implementations. We haven't really defined machine learning, and I'm not actually totally certain if everybody agrees exactly what machine learning is. The way it's used these days is almost anything is machine learning if it's an analysis. And but certainly clustering and is a machine learning, a typical machine learning algorithm. Neural nets, learning networks, and machine learning, and so on. Now, if I look at these use cases, particle physics or the radar analyses 43 and 44, they have domain-specific analysis, which is called signal processing for radar data. It uses things like fast Fourier transforms, classic algorithms. You would not normally call that machine learning. Although more and more, some of these analyses are using local, like in astronomy, they're using local machine learning components. By local, I mean you apply it to each point, rather than, so they're using the local machine learning just in the actual processing of the raw data points as well as in the overall discovery process, which is the global example of machine learning. Because if you're doing discovery and across the whole data set, that's where you'd expect to need global machine learning, because you're integrating the global results from everything. And remember, in the particle physics example, that global step ended up as histogramming, which is really not machine learning. It's too simple to be called machine learning. I have this classification called expectation maximization. I didn't actually write that down for any of the use cases. Many of them use it. The main reason I didn't do it is in most of the cases you can't actually tell whether they're using it. In some cases where they're using clustering, that uses expectation maximization. So it's I could have written it down. But in most cases, I couldn't find out exactly what algorithms they were using. Anyway, it's a class of iterative approach to optimization where you um, you do tractable analyses by making approximations in 2 steps. You have an iterative algorithm, you fix some of the variables, the values of at the previous iteration, find the values of the next iteration for other variables, and then in the maximization step, you find the remaining variables, and then you iterate this approximately, because you can't find exact optimization. So you do it iteratively by fixing and minimizing some of the subset. Already pointed out that the graph classification is important because there's a processing graphs is particularly tricky. A lot of the methods used for non-graph algorithms don't work very well because they're very irregular, difficult to predict structure, and that makes the whole calculation much harder. Collaborative filtering is possibly one of the most important algorithms ever invented. Remarkable how successful that is when used in Netflix and Amazon and places like that. And it's an approach for matching interests of one user with other users and tell you what data you're meant to investigate. And as we'll see when we study it, there are 3 subclasses: user-based, item-based, and content-based, and then some hybrid combination of them. So that's the end. So we've been through giving you a short discussion of all the things we use to classify those use cases, to tell you, and that's the idea, is to point out what things you need to put together and how they vary from case to case. And it maybe will help other people to classify further use cases, see what new cases are not captured in those 51, what features, and so on. Thank you very much, and I apologize for being me on all these slides. Thank you.